So we're going to try to get into gas turbines today. This is an image of a gas turbine, General Electric's gas turbine for stationary power. If you're going to burn natural gas to make electricity, you're going to do it not in a vapor power cycle, you're going to do it in a gas power cycle, a Brayton cycle. But before we get there, let's try and tidy up a few things in internal combustion engines. There's a metric, just how to measure both the Otto or diesel cycle performance, known as the mean effective pressure. It's just by definition the net work for one cycle divided by the displacement volume. And it has units of pressure, mean effective pressure, something kilopascal. You can change the compression ratio. It'll go up. MEP will go up. You could change the maximum temperature. Let's say in Otto, it'll go up. Okay. But it's just a metric, and a lot of times the problems ask you to compute it. How would you compute it? Get the net work divided by the displacement volume. Octane number. I think I talked about this last time, right? You have a choice when you fill up. You can pay a little bit more for higher octane, but what exactly are you getting? You're getting an increased resistance to knock. Again, to talk about the knock, it's before the piston gets to top dead center. The fuel could start to combust. The spark plug hasn't told it to combust. It's because of a hot spot on the face of the piston, a hot spot on a valve, a hot spot near the spark plug. And once that starts to go, and then you get the pop from the spark plug, you'll get a pinging. It's like a hitting. And it's very detrimental. I mentioned they have knock sensors in automobiles, especially for higher compression ratio engines. The knock sensor is detecting whether or not there's the onset of combustion not controlled by the spark plug. And it can lead to damage if the knock sensor isn't working. And then when it works, what's doing, it's going to retard the timing and cool back. You won't get as much power out of that engine. All right. This is an image of a knock sensor. This is another image of a knock sensor. Some engines used to just have one. Some engines have two. Some engines have one per cylinder. Anybody had a check engine light and go in? Oh, you got an out. Your knock sensor's out. Anybody? No? They're pretty robust, but they will go out. All right. I didn't know what year they had been put into vehicles, but I checked, and so the knock sensors have been a requirement of OBD2 since 96. They've been out for a long time, okay? Also, discussion about minimum octane number for your gasoline. Somebody in the AM section said, oh, the BMW, they require a minimum octane. So I looked up, I could get an owner's manual for this 525 sedan 2004. And the owner's manual says use lead-free gas only. Okay, that's great. You can't even buy leaded gasoline. But don't add the additive lead to boost octane. And it requires premium unleaded with a minimum of 91 anti-knock, or the octane number of 91. Do not use leaded gasoline. It could cause damage to the oxygen sensors and catalytic converter. I don't think you could buy leaded gasoline since about 82. I don't think you could buy leaded gasoline. I think that's about when it went out. All right. How many people know that they have high performance vehicles and they have a minimum octane? They can't buy the cheapest gas. They have to buy the more expensive. Nobody in this class? Only one? That's it? Man, there's a whole bunch of hands up in the AM class. They have better vehicles. You need to step up.
They have better parents.
Better parents, huh? No. Also, I thought, what's the highest compression engine available commercially in a vehicle today? And it looks like on a Mazda, this engine, which is a 14-to-1. Now, that's not a carbureted, it's not a throttle body fuel injector, not a multi-port fuel injector engine, okay? Where does the gas get in with the oxygen? It doesn't come in to the combustion chamber mixed. It's a direct injection gasoline engine. Direct injection meaning they have a fuel injector into the combustion chamber just like a diesel. They've been playing around with those for a while. It looks like finally we have one out on the market. I think this came out in 2012, but it did. You own one? You do? Oh, let's go for a ride. Cancel class. He owns one. Let's romp around. What? It's too small? It's high efficiency? Is the selling point performance or is the selling point miles per gallon? Really? Okay, so it's selling points miles per gallon. So you have a very high compression ratio engine for mass production. They've had experimental ones higher, and significantly improve fuel efficiency with that high compression ratio, high combustion. Let's see, 15% increase in fuel economy and torque, blah, blah, blah. This is straight off of their sales pitch. Okay. Are you happy with it? Yeah. But it's a really small car. It's a Mazda 3, it's just too small. So that means if the high winds, you get blown over sideways? One of those cars? Ever drive one like through a crosswind? You're fighting. Yeah. If you own a diesel, anybody fill up with diesel? You have the cetane number. And a lot of times you come up to the pump and it looks green like this, and maybe they'll say on the handle, here's a 87, for the octane, the gasoline, but they'll just, oh, it's number 2 diesel. Or maybe you'll look and it'll have the label up here, oh, it's number 2 diesel. But every now and then they'll actually rate or show you the minimum cetane number for the diesel. Okay, here's another pump where it's shown. But probably in a lot of states it's not shown in a lot of locations. I don't buy diesel very often, so I've not really looked at the pumps. Do you look at the pump? Are you familiar with the cetane number?
Yeah, it didn't say. I usually fill it at
Doesn't have it. So a lot of pumps don't have it. Well, it's a measure of a property of the diesel, and it's related to ignition, okay? Just like the octane number. But the cetane number is a measure of the ease with which the fuel is ignited in the engine. It's insignificant for low temperature stability, for warm startups, or cold startups, for smooth and even combustion. The cetane number should meet your engine manufacturer's minimum recommendation. Well, the manufacturer of gasoline engines, if you want a performance engine, they'll make it, but you have to put in the minimum octane, and they tell you. There's not too many performance diesels. It's like it used to just be a workhorse, and so the minimum is typically a 40. There's no people going like 44 or 45. That's why there's just one grade of diesel. Just there it is. The cetane number does not materially improve the engine efficiency or the operation, nor does the octane. The octane just lets it, if you have a higher octane number, you can run a higher compression ratio in it, right? And then you will have a better, higher efficiency engine. But let's say you put in the same grade gas into a low compression engine, or different grades of gas, you will not see a higher mile per gallon if your engine doesn't require that higher octane number. Most engine manufacturers recommend a minimum of 40. And this always kills me. Diesel fuel sold by reputable marketers. What does that imply? There's some disreputable marketers. Where are the disreputable marketers? I don't know. Where are they at? It just implies there's disreputable marketers, and I don't know of any. Did we sketch out the diesel cycle on the PV and TS diagram? We did? Let's go 1, 2, 3, 4. 1, 2, 3, 4. If you have the heat addition right here, Qn, that's Q2 to 3. That's going to be a C sub P, T3 minus T2. Not a C sub V. Okay, because as it's burning, as you have heat addition, you also have work out from 2 to 3. And this Q from 4 to 1 is negative, but it's C sub V, T1 minus T4. This will be a negative quantity. So let's go ahead and derive this equation right here for the thermal efficiency of a diesel cycle, assuming cold air standard analysis. What's in the equation? Take a look. What are the parameters? Eta, thermal efficiency, R, compression ratio, R sub C, cutoff ratio, and K, which is in 3 places. What's K? Ratio of specific heat. So as a starting point, what I would do is I would sketch out on the PV diagram the cycle. 1, 2, 3, 4 for the states, and the processes between them. And we're very much going to be interested in heat addition. 2 to 3, Q to 2 to 3 is going to be a positive quantity, and we already discussed where it's C sub P T3 minus T2, right? If you do a first law analysis of the process, 2 to 3. Likewise, Q 4 to 1, right here coming in, it's going to be negative because T1 is less than T4. This is a negative Q 4 to 1. The thermal efficiency is defined as work net divided by Q in, Q2 to 3. Is that true? Thumbs up if you agree. Is that good? What's R? Compression ratio. Is it V1 over V2? Is it this volume or specific volume divided by that specific volume? Is that the compression ratio? Yes, thumbs up. What is R sub C, the cutoff ratio? Is it V3 divided by V2? Will either the compression ratio or the cutoff ratio be less than 1? No, they're always going to be great. And typically this is around 20 and this is around 2. Okay, but they're both greater than 1. And the ratio of specific heats is given. So how do we start this analysis? Well, we're asked to derive eta as a function of everything else on the right-hand side of that equation. So start with eta. It's equal to the work net divided by the heat in. Is that also equal to Q net divided by the heat in? That's right. Is Q net equal to Q2 to 3 plus Q4 to 1? Is it? Is that now equal to 1 plus Q4 to 1 divided by Q2 to 3? It is. And look at the form. We've got this 1. Then we have some plus or minus the rest. This will be a negative. So if you want, put a negative right here, put a negative in front of that 4 to 1, because didn't we say Q 4 to 1 is negative? So a negative is a positive. Right? So now we have that form of our equation. So this is what I just did over there. So I have plus Q 4 to 1 over Q 2 to 3. And I substitute that form for Q 4 to 1, this equation for 2 to 3, and there I go. True? All right, if I do that, now what do I have? I have 1 minus, what is C sub, isn't that 1 over K? That ratio of C sub V over C sub P, that's 1 over K. And now I have these temperatures. This is where experience comes into play. What's experience? I've done this before, right? Have you done it before? No, you have no experience. So let me just show you what experience would suggest at this point. In the numerator, pull out T1 so that it becomes T4 over T1 minus 1. See how we pulled out T1 in the numerator? In the denominator, pull out T2. so that you get T3 divided by T2 minus minus 1. I pause, I stop. Did you follow that algebra? At this point, what we can do is we can get relationships for these ratios of temperature. All right? So here are the equations for the ratios of those temperatures that are going to be useful. First one may be, just recall, how did the difference between the ratio of temperature T2 over T1, if I'm going to compress it isentropically, S equal to a constant, is this equation true? If that equation is true, then if I ever see the ratio T2 over T1, I can replace it by the compression ratio raised to the K minus 1 power. Okay? How about this ratio? Well, it looks a lot like this ratio. They look similar, but I'm going from state 3 to state 4. Instead of compressing from 1 to 2, I'm expanding. Am I not? And I'm expanding from 3 to 4, so it's a very similar equation. Isentropic, S equal to constant. It's just that my specific volumes are different. I go from specific volume 3 to specific volume 4. So I have, if I now put 2 over 2 right here, I didn't change it, but that ratio, V sub 4 over V sub 2 is R, and V sub 3 over V sub 2 is R sub C, so I get that T3 over T4 is compression over cutoff ratio raised to the K minus 1 power. We're not done. Also, the cutoff ratio is V3 over V2. I replace V3 by here. I replace V2 by there. What did I just use? The ideal gas equation. Hence, T3 over T2 is the cutoff ratio. So what I can do is use those relationships. Do this on the side. Get those relationships for the ratios of temperature, and now finish out the algebra. So this is where we left off. Take that T4 over T1 and say it T4 over 3, 3 over 2, 2 over 1. See how that happens? And then say, 4 over 3. Let me look up here. You know what? Right there. 2 over 3, or 3 over 2, right there. And 2 over 1, right there. So all three of those will come into play in that expansion. The 2 over 3 right here is the cutoff ratio, so that's done. So the numerator takes more work. And so in the numerator you get the multiplication of these three terms, this one, this one, this one. And then what you do is you just simplify, and then you have R sub C times R sub C to the K minus 1. So that R sub C cancels with the K, the R sub C to the minus 1, leaving only R sub C to the K. And there you go. So to make it look like the textbook, what we have is we just move that K inside like that. QED. Is that helpful? I suggest as you get good at solving Otto and Diesel and Brayton cycle problems, just like this. It's given to you in words, and you have to sketch that PV diagram from memory, recall first law, how to apply it for each of the processes, etc. So here is a air standard diesel cycle. Starts with 98 kilopascal and 300 K at the start of the compression stroke. So that's going to be state 1. So down here at state 1, before it goes to state 2, from 1 to 2, they know the pressure and the temperature at state 1. Then you come across to state 3, so make a sketch, right? There's 4, and there's the whole thing. You probably want to make a table, state 1, 2, 3, 4, pressure in kilopascal, we just fill in the 98, and the temperature in Kelvin, 300. And if you want, you can put specific volume. It's just not needed. And then I also make a table of the processes, 1 to 2, 2 to 3, 3 to 4, 4 to 1, and then I always leave a little after it's net, sum the ones above, sum the Q's in kilojoule per kilogram. I'm not using parentheses. Let me try that again. That's not bad looking. Q. Boy, I can't write today. Get a Q down there. Q, comma, kilojoules per kilogram. Get a work in kilojoules per kilogram. And if you want, you can get a delta U in kilojoules per kilogram, but I'm running out of room. Okay? What's the change in internal energy? Okay. Let's continue to read this. They have the compression ratio is 19, the cutoff ratio is 1.9. On the basis of cold air standard analysis using this value of C sub V and this value of C sub P, determine the temperature at the end of the compression stroke. So we want to find T2. The peak pressure, that's either P2 or P3, that's same pressure. The peak temperature, that's only T3. And the heat addition to the cycle, Q2 to 3. The net work of the cycle, W net, you can calculate it by getting Q net or the sum of the works. Either way, it should be consistent. And the thermal efficiency, the ratio, the answer from part E divided by part D, the answer from part D. So we recall our equations. How do I calculate T2? What's the equation for T2? Which is it? Well, you would, I know that they're, let's see if I have the, oh, come on now. Here. Right? So if I have an ideal gas undergoing isentropic process with constant specific heats or constant ratio of specific heats, which implies the same thing, then if I want to get the T2 over T1 related to P2 over P1 or T2 over T1 related to V1 and V2, etc. Use this one right here for that first process, right? All right. And then use this one for part B. So T2 is equal to the compression ratio to the K minus 1, and P2, whoops, left off the T1 there, is equal to P1, the compression ratio to the K. This is 20. Where's this at? So we find that T2 comes in, let me just add it to the table, 972.2 Kelvin. And the pressure comes in at 6034.1 kilopascal. So that's the answer for part A and B. Now this, how do I get P3? It's the same as P2. How do I get T3? How do I get T3? Use the ideal gas equation that V2 is equal to V3, and that's equal to RT2 divided by P2 is equal to RT3 divided by P3. Cancel the R's and solve for T3 is equal to T2 times start over again, Professor. Do this one. What is the R sub C is equal to V sub 3 divided by V sub 2, right? Now use the ideal gas equation, RT3 divided by P3, RT2 divided by P2, cancel the R's, cancel the P's because the pressures are the same, and we find that T3 is equal to the cutoff ratio times T2. And so that temperature jumps to 18 47.2. And then for T4, just like the isentropic compression, it's isentropic, S equal to a constant, S equal to constant expansion, and we calculate that it's 240.6 and 736.5. Notice this pressure at 4, right before you're modeling the what is that? The blowdown followed by the exhaust stroke, followed by the intake stroke. That pressure is greater than atmospheric pressure, and so that's why you have a large rush out when that valve cracks. In the analysis, we just begin a constant volume cooling. Okay, so we can then solve for the Q's. This is 0, right? The heat transfer from 2 to 3 is the specific heat constant pressure. That turns out to be 880. And then it's 0. And then it's negative 313.7, leaving a Q net of 566.3 kilojoules per kilogram. Similar for the works, but I already have the answer for part C and the answer for part D, and the work net's equal to the Q net, so we have the answer for part E as well. And then thermal efficiency at the very end is the ratio of the answer for part E, which is 566.3 kilojoules per kilogram, divided by the heat addition in Q2 to 3, 880 kilojoules per kilogram, giving us a thermal efficiency of 64.3%. What happens if I use that analytic expression? You get the same value. You should check. Check that the work net and heat net are the same. That's a good check. And also check if you have an analytic expression for the efficiency, see if it agrees. Here are the numbers run in Excel. All right? So in Excel, we get that 64.3% calculated with these numbers above. These are consistent. And the analytic expression gives the same. One thing is this is a cold air standard analysis. It uses an average temperature of 300 Kelvin. I can look up or evaluate specific heats at higher temperatures. What happens if I wanted to do a warm air standard analysis using a constant specific heat evaluated at a higher temperature? It would give a better answer. Okay. What temperature should I use? Well, it started at 300, went to 900, 1800, 700. Just take these temperatures as a crude approximation, get the average temperature of those, and redo it. So if you used an average temperature of 964 Kelvin, evaluated the C sub V and C sub P for air at those two temperatures, at that temperature, these two values come in different. See how that's changed? So 1.005 to 1.139. Doesn't look like a big change, does it?
That was the only difference between the cold and the warm. I mean, all the assumptions from the cold.
That's right. You just use a constant specific heat for the whole cycle based on a higher elevated temperature. The ratio of specific heats is now, instead of 1.4, maybe 1.338 or 337. Doesn't look like a big change, does it? But look at the difference, 566 versus 482 in the Q. That's a big change, isn't it? And they are consistent, that's good. And the thermal efficiency is now 58%. So don't take these percentages used by the simple diesel cycle approximation cold air standard analysis. Take that as money to the bank. It just gets you, it shows you the behavior of the system. There's a great plot in the textbook which shows as a function of the compression ratio R, If you increase the compression ratio, what does the thermal efficiency of the Otto cycle do? Goes up. So for high performance engines, boost the compression ratio. Likewise for diesel, the same trend. Here they also have different cutoff ratios, okay? So there'll be a couple different lines of cutoff ratio. I think if my memory is correct, is this R sub C goes approximately to 0, and then increasing R sub C. As R sub C goes to 0, and somehow you make the maximum temperature go up, you specify that maximum temperature, then that diesel cycle looks like the Otto cycle. All right. One of the benefits of the diesel cycle is you can run the compression ratios in the order of 20, 22 or more. All right, ready to speak a little bit about gas turbines and power plants. So if I want to make electricity in the year 2013, 2014 in Texas and throughout the nation, and I want to build a new power plant, I'm going to build a gas-fired power plant. I'm not going to build a coal-fired or coal plant. I'm not going to build a nuclear plant. I'm not going to build, other plants. I'm going to build natural gas because it's economically the cheapest out there. And when you burn natural gas to make electricity, you don't boil water. It's all as an ideal gas. So you bring in some air and you put it through a compressor. Typically these run on the same shaft, but it doesn't have to. And you boost the pressure. So the pressure at 2 is greater than the pressure at 1. And you now talk about the pressure ratio P2 over P1. We don't talk about a compression ratio. We talk about a pressure ratio. Then we put it through the combustor where a little bit of the fuel is added in the combustor to the air, and it's fireball, and the pressure at 3 is equal to the pressure at 2. It does not change the pressure in the combustor, but it's spanking hot. Because it's hot, it's like its volume is expanded, and now it can push a lot of blades on the turbine and expand through the turbine. So as it expands, now you go down to the low pressure, P4 equal to P1 atmospheric pressure. And then typically you exhaust it, because the combustor, when you add fuel, what is the fuel for natural gas? CH4. Isn't that methane? It's primarily methane, 99% methane, 98% methane. Okay, and so you'll get some nitrogen from the air. You may have some excess oxygen that wasn't used in the combustion. Hopefully all of the carbon goes to carbon dioxide. Hey, doesn't the EPA want to limit carbon dioxide emissions? Sure does, but if you're going to burn a hydrocarbon fuel, that's where you want the carbon to go. All right. And then the hydrogen in the fuel goes to water vapor, H2O. So that's what's coming out. And then you just do something useful with this warm exhaust gas. Maybe you combine it with use it in a boiler for a vapor power cycle. So you have a combined cycle plant, and that's what they're building. They're not going to build just only a gas turbine unless they're really pinched for money. They're going to build a combined cycle plant. Well, what do we do for the analysis? We do an air standard Brayton cycle. There's no combustion products. It's always an ideal gas. The combustion is replaced by a heat transfer in a heat exchanger from an external source, Q in, and the exhaust and intake are replaced by Q out. Just a heat transfer. You can also add the additional cold air standard analysis where you're saying everything's constant specific heats at atmospheric temperature 25 C or close enough to 300 Kelvin. So we close the loop. And then we do an analysis of each component. What type of analysis would we do for a compressor? What type of analysis would we do for a heat exchanger and for a turbine and for a heat exchanger? Much different than the Otto and diesel. We would do an open system analysis for each component, where for the processes in the Otto and diesel, it was a closed system, trapped amount of gas that was compressed, heated, expanded, cooled. Here we have gas flowing through one component that's compressed. Its pressure is boosted. Then through another component where it's heated, through another component where it's expanded, and another component where it's cooled. But you do an open system analysis for Brayton cycle. Professor, are you ever asked in your office to please explain why we have, delta H's instead of delta U's? Auto and diesel, it's almost all delta U's. Here you have all delta H's. That's why. It's an open system analysis. You have the change in internal energy as well as the change in flow work, the PV term, when you have a control volume. So this work into the compressor is, do the first law, H2 minus H3. Do you like that? There's no heat transfer in the compressor. Neglect changes the kinetic energy. The work per unit mass is the change in H. How about the Q in? That'll be H3 minus H2. How about the work out of the turbine? That's going to be H3 minus H4. And I know I do this quick, and I know the average student needs to go slowly and be careful about this, okay? Yes, sir. Yeah, I messed that up. So it's H2 minus H1. You're right. Thank you. Does that look good now? All right. And then this one is H4 minus H1. True? How many people have, been in a class where you don't suggest a change to the instructor? If they made a big mistake, you just let them go, because if you raise your hand and point out the mistake, you don't know what happens, but usually not good, right? You been in a class like that? Yeah, okay, we all have. I always try to, every time I teach a class, I try to help students, because I know that when you get out of here, you'll need to engage with other people. And you'll engage to kind of convince them, maybe on your design team as close experience to this. But in the workplace, it's really important. And they come up with some idea, or they do something. It's like, it's wrong. But you want to gently correct your coworker, or gently correct your boss. And you got to be careful, because unfortunately, some coworkers and some bosses are like some faculty. They don't like to be told they're ever wrong, and they blow up, right? And they become wild cannons. So whoever did that, it was great. I know the number of hands up. You got to gently do that, But there's some other students that maybe they usually sit in the front row. Nobody's in the front row today, right? So I can say, yeah, they always sit in the front row, and they're like, "Ooh, you made another mistake!" It's like that's gasoline on the fire. It just blows up. It's not good. I haven't had one of those students in a long time, but I have had them before. It's like, congratulations, you found another error in my lecture. Keep watching, there'll be more. There'll be more. Okay, I think I have this right. So now what we need to do is get the things like the work net. You can do it two ways. You can just do the work of the turbine out minus the work in the compressor. Notice that I left this to be a positive. It's hard working with negative quantities. We like to work with all positive quantities. Or you could also say that's equal to Q net. They're equal. And the Q net in is Q in minus Q positive out, right? That's a positive. This is positive out. Okay. And then the efficiency of the cycle is the work net divided by the Q in. So we just need to analyze these systems and solve problems using these very similar equations that we used for the Otto and diesel cycle. It doesn't matter if it's a trapped amount of gas undergoing an isentropic process, or the gas flows through the component undergoing an isentropic process. If it's isentropic, it's isentropic. Okay? But you'll find that this is used more often for the Brayton cycle because we have pressure ratios. And This one's used more often in the Otto and diesel cycle because it's compression volume change ratios, right? Okay, so there's a distinction. Well, we could solve a problem, but we're out of time, so I'll pick up there next time. Thank you.